Let's consider something a little more complicated. Let's consider beam loading. If in statics all you did was study two force members, you might have wondered, well, what happens when a beam or a member is loaded transversely, right? When it's loaded perpendicular to the axis through the member. Well, then it's a beam. That's how we define a beam. It's any structural element that is loaded perpendicular to its long axis. So you see this beam and a spring and a hydraulic cylinder from a side view, and then the schematic drawing of it with the force from the cylinder, the force from the spring, and the reaction at the pin. And certainly this beam is being bent, right? So it's not just a beam or a member that's loaded axially, it's loaded cross to the axis. Now there can be several different types of loads on beams. If you look at this beam that's holding a bunch of pipes, okay, it's just suspended with some maybe wire rope or whatever it is, and the pipes are hanging down on it. In that case, we could consider each of those pipes as a perpendicular load, something that is perpendicular to the beam axis itself, and of course there are reactions in the cables holding the beam up. So these are just perpendicular or normal concentrated loads that are applied to the beam at points along the length of the beam. Now what about if the line of action is at an angle? What if it's got some axial and some normal component? Well, you already know how to deal with the axial component in statics, and all that does is cause either tension or compression in the beam material itself. The piece we're really interested in is that normal piece. So we can take a force that's at some other angle and basically just break it down into two parts. Just decompose the vector into an axial and normal direction. Now another type of load that we'll encounter quite a lot are uniformly distributed loads. Now these are loads that aren't point loads, but they're loads that act over a length of the beam. It doesn't have to be the whole length, it can be sections of the beam, but these are distributed loads. And you know, if you think of something like snow on a roof that's even, or even if you think of a floor, for example, a floor where people might gather on the next floor up, or people that gather on the roof, or however, just on top of the beam, that would be a distributed load. As a matter of fact, people are often modeled as distributed loads in a lot of design. It's kind of interesting in that kind of design. There's something called the live load and the dead load. I believe it's called live and dead load. And it's something I had to do. I filled in my middle room when I bought my house. It had a center room that when it was designed was opened outdoors, but it had been covered. So it was sunken in. It was a big pain. So I decided to cut the concrete out that was in there, because there's actually dirt below the level of it. Cut the concrete out that was on top of that and put beams in and make the floor level. Well, I had to consider two parts to that load, that transverse load on the beam. One part was people walking across it, right? Or my piano, for example, that I put in there. And the other part was the dead load. And the dead load was just the uniform load from the layers of plywood I had to put down, the ceramic tile, and the underlayment under the tile that was required. And so that all is dead load. Now if I remember right, actually technically the piano and couch and those things would all be considered dead load, because they don't move, they're static loads. But the live load is, say I had a party or something, had a whole lot of people in that middle room, well then that would be a live load. They'd be moving around and could even possibly be modeled as a distributed load if there were enough people. Now what about distributed loads that vary? Not all distributed loads are uniform across the entire beam. And a lot of times you might think of snow as a distributed load. So you can see the beam sticking out from the building. There's snow on top of the building, or I'm sorry, on top of the beam. And this could be an overhang or something where the beam is supporting the load. But you can see how the snow tapers down, and most of the time with something like this we would model it as a linearly decreasing load that has some maximum at one end and goes to zero at the other. You can put multiple loads together. Here's two varying distributed loads back to back, and we can model this as well. And this is about the most complicated it will get. In the real world you might vary it continuously changing, and there are integral equations for dealing with that, but we're interested in simpler things in this class. We're just interested in understanding how this topic works. What about if you have other kinds of loads besides forces? Could you have moments on it? Well, yes, you could. And here you see a beam where the horizontal portion is the beam, and there's just some section of the beam sticking up to provide a moment arm where two forces are applied as a couple, causing pure rotation. And so basically the entire beam has a pure moment in the center that causes the shape of the beam to deflect. So this is a concentrated moment on a beam. Now there can be many different types of supports for beams. There are simple supports, and you should be familiar with these from statics. Simple supports, of course, resist forces in the perpendicular direction, the cross direction of the beam. They don't provide any resistance along the axis of the beam, and of course they allow rotation. Whereas pinned supports allow rotation but can support loads in both the perpendicular and parallel to the axis of the beam directions. Fixed supports, on the other hand, don't allow any rotation where the beam is fixed, and they can also provide force in any direction, horizontal or vertical. Now there's a couple different types of beams we will define. First of all, there's the simple beam. This is a beam that only carries loads that are perpendicular to the axis and has simple support, so no horizontal resistance, just all perpendicular loads. Now these loads could extend beyond the supports, in which case we'd call it an overhanging beam. So you see here a couple of supports in the center with reaction forces R1, R2, and then the loads to be supported, F1, F2, and F3. Well, F1 and F3 overhang the supports. Cantilevered beams, on the other hand, are where one end of the beam is fixed, and that's it. That's the only support it really has. So there's a fixed connection and then load at various points along the length of the beam. Those could be loads that are perpendicular to the beam. They could be concentrated moment loads. Sometimes we'll even have axial loads on these. Now a compound beam is a beam where we have more than one just single beam axis. We have portions of the beam extending in different directions, and this is only important when there's loads on that portion of the beam. So we've already seen an example of it, but you could have, say, an L-shaped beam that goes up over, well, I guess that's more like a Z-shaped beam. So you can have all sorts of different shapes, but really a compound beam is where we have multiple different directions of loads on multiple segments of the beam. Continuous beams can have more than two supports, and a lot of times we end up with statically indeterminate type beams. So you notice here we've got external applied loads 1 through 4, and yet we have 3 reactions. Well, we don't need 3 reactions, at least from statics. How do you solve a problem like that? Well, that's one thing that strength of materials can answer, is how you solve a beam like this that is statically indeterminate. Alright, so the first thing to do when you have a beam is always to calculate the reactions at the supports if you can with statics. If it's a statically indeterminate beam, then it takes a little more effort. There's some other equations and things we can use that take into account deflection. But the first step is to draw a free body diagram, and then some moments about one of the supports to find the reaction at the other. You know this from statics, hopefully. Do the same thing for the other support. That way, in the fourth step, you can check your calculations by summing the forces in the y direction to ensure that they all come out to 0, as they should, if you've summed your moments correctly. The reason for taking both sum of moments is those are harder, but you have to use one anyway. And so if you use 2 sum of moment equations, you might make a mistake, but you'll catch yourself with a sum of force equation. After that, of course, what we'd like to do is draw shear and moment diagrams, because the shearing force within the beam material and the moment within the beam is what will tend to cause the beam to fail, not really the external loads. The external loads cause the shear and moment in the length of the beam, but the largest loads within the beam material may not be where the loads are applied. It could be where the reaction is. For example, a cantilevered beam with a load out at the end has a very large moment reaction at the base of the beam near the fixed support, and that's where the actual failure is most likely to occur. So we'll talk quite a lot about shear and moment diagrams. I've got plenty of examples for you on that. You've probably done a little bit with this before, but we'll go into a lot more depth and refresh your memory and maybe take you a little farther in the example problems.